Now, so very good afternoon everyone. I hope you all had a good lunch. In this lecture we'll talk about the metastable states and phase stability. So in this lecture what we'll cover is we'll cover what the different phases are, how the phase change occurs, what is the role of metastable states in the phase change, and if these states are stable or not. This all we'll discuss in this lecture. So to start with, we all know from our experience that all the matter, all the pure substance, they exist in different states. We see water in this water bottle. It is right now in liquid state. If I put the same water bottle inside a freezer, it will convert into ice, which is a solid state. And if I put the same water on the top of a heated surface, which is heated above 100 degrees centigrade, then it will convert to a gaseous or vapor state. So it means that all the pure substance, they exist in three distinct states, and they have different phases, right? All the three are different phases, which depends on in what way the molecules are arranged. So in the terms of a solid state, the molecules, they are packed very closely. In fluid, the molecules are again packed closely, but they can flow. In the terms of in gaseous state, the molecules are loosely packed here. So phase in terms of thermodynamics, it can be defined as an open region in thermodynamic state space where system properties such as your Gibbs free energy or any thermodynamic potential, it is both analytical and homogeneous. With analytical, by analytical we mean that it is continuous, it is differentiable at that region, and also it is smooth. So phase is a homogeneous region of system with uniform physical and chemical properties, and as I have discussed, water, it exists in three phases: the ice, water, as well as steam. Now to determine which phases are stable under what thermodynamical variables like temperature and pressure, or at what lines the phase change occurs, or are there any landmark points such as the critical point, or at what conditions these landmark points exist, like the critical or the or other points. So we need a phase diagram to discuss that. So phase diagram is nothing but a graphical representation that shows the stability regions of different phases of a substance as a function of thermodynamic variables like both temperature and pressure. So here in the figure you can see a pressure temperature diagram, which is also known as the phase diagram. In this phase diagram, the three different regions are demarcated by lines here. So we have three distinct lines. One is a sublimation line here, one is the melting line, and one is a vaporization line. And in all these areas we have a distinct phases. So if we talk about this region here, we'll have solid phase, or let us talk in terms of water. So let's suppose that we are presently at 0 degree centigrade and the pressure is 1 atmosphere. So it will be somewhere here. It is 0 degree centigrade and this is your 1 atmosphere. Before this state, we'll have at lower temperatures at 1 atmosphere, we'll see that ice will or solid form will exist. But beyond this point on this phase diagram, we'll see the melting will commence and we'll see liquid water. Further, as we move on the same pressure but at 100 degrees centigrade, the liquid will convert to steam here. So this all information we get from the phase diagram. In addition to that, we have several landmark points like the critical point here or the triple point. Well, triple point is defined as a point where all the three lines meet. It is a point where all the phases they can coexist. On the other hand, this critical point is defined on the vaporization line, and beyond this point, we cannot distinguish between your vapor as well as liquid. In the case of water, we cannot distinguish if it's liquid water or if it is steam. And for water, this point is at 374 degrees Celsius, and the pressure is 217 atmospheres. So this is all about the phase diagram. I'll also briefly talk about the PVT surface here, because in the later stages of the lecture we'll discuss more using the PV diagrams. So PVT surface, it gives us the exact thermodynamic description of a system. For what pressure, for what temperature, what is the specific volume that is required when we talk about phase change. So if we see the projection of this PVT surface from this direction, we will get the PV plot. Its projection from this side, it will give us the pressure versus temperature plot. So in brief, the PT diagram is just a trailer of a movie, and PVT is the whole essence, it contains the whole essence of the thermodynamics which is happening in the system. Moving forward, so let me also talk about little bit about metastability here. Of course, we'll discuss a lot about this in our next slides, but a phase is stable if it corresponds to the lowest Gibbs energy at a given pressure and temperature. On the other side, the metastable state is not the most stable state. So if I plot here the G versus state diagram, so for any given state, for any given pressure and temperature, we might have different states here, right? So if you see this G versus X plot, this is a point of global minima. It means here the Gibbs free energy is minimized. Now, what about these states or these states? It is still the minima. Here also the dg by dx is 0 and d2g by dx square is also greater than 0. But these states, they are not the global minima. So these are the metastable states. If enough fluctuations, if enough perturbations are given to this system at this state, they can transition to this state. But right now they are stably placed. At these states. So these states are called the metastable states. A system is trapped due to energy barrier which is preventing the system to transition into the stable phase. And at these points, the entropy is not totally maximized. We know that at a stable state, the entropy is maximized. But at these states, the entropy is not maximized. It will have maxima at the global minima where the Gibbs energy is at the minimum point. So we can have more microstates which are not observed at these metastable states. Why are we studying this? What is the importance to study these metastable states and phase stability? Well, their knowledge is both important for engineers as well as for researchers. They have got application in mostly all the domains which are covered in mechanical engineering. Let's talk about the boiling and condensation heat transfer. Here, if you want to control the nucleate boiling, it is better to have knowledge of metastable states and phase stable. At what points we have metastable state and what points we have a stable state, and what energy is provided, what energy must be given so that the phase change can occur. So that is one importance. Applications also in the case of thermal management of electronics, where right now we use microchannel based cold plates, where the two phase flows occur. It means that we have boiling occurring at that place. That plates. So this knowledge can also be applied to those sections. At low temperature physics like cryogenics and superconductivity, here we need to see whether the states are they are stable at certain lower temperatures. That also can be known from this knowledge. In refrigeration and air conditioning as well, we have application because it is desirable that the stable phase behavior is observed over the entire operating range. So if we have idea about metastable state, at what point metastable states exist, then we can make sure that our system, it doesn't leave the stable state operation at that period. Also very useful for heat treatment of metals. Reason being that in the heat treatment of metals, for certain temperatures, metastable states exist, and those states, they give exotic properties to the metals. So we must know that at what temperature, at what pressure those states can exist, so that we can tune the properties of the metal in which we are working with. And lastly, the thermal energy storage systems. Here also the phase stability is important because these thermal energy storage systems, they are basically the phase change energy storage systems. So now we have revised what is phase, at what points, and according to classical thermodynamics, the phase change occurs. Now let us talk about the metastable state and phase stability. Before going forward, let us briefly discuss about the microscopic uncertainty. So when we talk about any fluid and we define its properties, we assume that at microscopic scales, these properties are well defined, they are constant over the entire range. So we don't see a lot of fluctuations, or even if the fluctuations occur, those fluctuations are very close to the mean value. So let's consider this room here. In this room there is air everywhere, it's completely filled with air. Even if a small fluctuations occur here because of the movement in my hand, it will not change the mean value of the density of the air inside this room. But if we talk about the microscopic scales, where or molecular scale, where the number of atoms are very less. So let me consider a small box here, and let us assume that at any given time, the number of molecules in this cube is in the order of, let's say, 10. Now, because of the random motion of these molecules, what will happen is in this controlled volume, molecules will enter, molecules will leave. So like fluctuation can occur that at any given time, 3 molecules they left this space and only 1 could enter this controlled volume. So it means that there is a fluctuation around 20% of the properties. That fluctuation is really high in case of states. So to define the fluctuations, what we use in statistical thermodynamics, we use basically variance. And variance, it defines what is the spread of the property in that for the given property. Yes. So why I am discussing all this is because later we will see that these minor fluctuations, they might lead to the onset of phase change. So that is why we are discussing these minor fluctuations, and we will talk a little bit more about the variance of properties such as variance in the number of molecules or variance in the internal energy of the system. So let us go there. But before going there, let me first define what my system is. So let me consider a system here. In this system, we have one more subsystem. This subsystem has porous walls, but the walls are rigid. So you can consider any porous structure, but its walls are rigid. So it means it has a fixed volume. But at the same time, because of the porous walls, both mass and energy, it can leave or enter the system. On the other hand, the subsystem 1, which encloses the subsystem 2, its walls are rigid. So this is an isolated system, that is an open system. Also its walls are rigid. So in this case also the volume is fixed, but at the same time, in this case the mass and energy, they cannot leave the system. It means that for the whole system, your mass and energy are conserved, they are isolated with the universe. And this system, it consists of a pure fluid. And also we assume in the beginning that subsystem 2 is in equilibrium with subsystem 1. Now what is the implications of these statements? Subsystem 1 is in equilibrium with subsystem 2. The major implication is that all the thermodynamic variables like your pressure, temperature and chemical potential, they will be same for both these subsystems because we have assumed that they are both in equilibrium. Right? Now, if we have to define the variance of number of molecules in a control volume, which is this subsystem 2, using statistical thermodynamics, we can define it as sigma n square is equal to kBT times del n by del mu at constant volume and temperature. Here Kb is the Boltzmann constant, T is the temperature, n is the mean value of number of molecules, and mu is the chemical potential. Well, using Maxwell relations, we can simplify it further, and we can write as sigma n square is equal to n square kBT by minus del P by del V at constant Nt times V square. In this, here we have P is pressure, V is volume, n is the number of molecules. Similarly, variance in the internal energy in controlled volume, it can be defined as n kBT square Cv by Na. Here Cv is the molar specific heat at constant volume, n is the Avogadro number, plus sigma n square del U by del n whole square at constant volume and temperature. Now let's see what insights we can bring from these two relations. Now since we have defined variance, and variance must always be a positive quantity, right? So let me first focus on this term here. Here this n kBT, they are all positive. V volume is also positive. So the sign of this term will depend on whether this del P by del V, is it greater than 0 or less than 0, right? For this term to be valid, minus del P by del V, it should be a positive quantity. At the same time, this should be finite, right? So first implication that minus del P by del V, it should be positive and finite, right? If we make sure that this is positive, this is both positive and finite, then this term will further be in the variance of the internal energy in the control volume term. Here again we say that we see that n kb t square Na, they all are positive quantities, and Cv is also positive quantity. Negative Cv is not possible. if we add energy to any system, its temperature cannot decrease. So Cv is also not a negative quantity. Further, U and N, the energy of a system and number of molecules, they both are also positive, and of course it's also a square there. And the sigma n square is there. What we can see here is that even though if this term is a positive quantity, but its magnitude is small, that will lead to very high fluctuations in the number of molecules or the density of the system, and that further will lead to fluctuations in the internal energy of a system. Even though the system is in equilibrium, but we can still see that the magnitude of this term minus del P by del V, it will govern if the fluctuations are huge or they are small. So that's what we'll see that minus del P by del V at constant n and t, they can become small enough to produce high fluctuations, and we'll also discuss this further. So I have discussed these things. Yes. So now virtually for all the real systems, Cv is a finite, we have discussed that, and it's greater than 0, and its value doesn't contribute to a high or unrealistic fluctuations, but the value of minus del P by del V, it does, right? So sometimes it may lead to produce high fluctuation in the subregion of a system, which can lead to the phase change. Now for the above stated system, which is a pure system, it is a closed system, it is possible to encounter circumstances in which the conditions for equilibrium are met, but the fluctuations in energy and density are large. Although we have assumed that the system is in equilibrium, but we have not yet explored the stability of the equilibrium within the system. So question is relevant because for high fluctuations in density and energy, these fluctuations may be large for the transition of the state to occur. So now doing that, by the definition of our system is defined to be as a closed system. We can say that the entropy should be maximum at the point of the equilibrium. So using the entropy maximization condition, we can write that ds is equal to 0 for subsystem 1 and 2 be in equilibrium, for subsystem 1 and 2 to be in equilibrium, right? Now further, we know that entropy, it's a function of your internal energy, your volume, and as well as the number of molecules. But in this case, our volume is fixed. So it is not a function of volume, it is just a function of your internal energy and number of molecules. Now for any perturbations that occur in your internal energy and number of molecules, let's suppose that perturbations del U1 in subsystem 1 and del U or del N subsystem 1, they occur in the system. That will lead to the fluctuations in entropy as well. So we can write the fluctuations in entropy as a Taylor series expansion. So we'll write it as delta S for subsystem 1 is equal to as Taylor series expansion S1 plus 1 by 2 factorial del square S1 plus 1 by 3 factorial del square S1 plus so on so, right? And here we can also define, I think it's given in the next slide, yes. Here we can also define these terms. So del S1 will nothing but be the partial derivative of the terms on which it is depending. So we can write del S1 as del S by del U at subsystem 1 times del U1 plus del S by del N F of subsystem 1 times delta N1. Similarly, we can write it for del 2 S1 as del 2S by del U square for subsystem 1 times this del U1 whole square plus del 2S by del U del N times delta U1 times delta N1 plus del 2S by del N square of subsystem 1 times delta N1 whole square. Similarly, we can also write it for subsystem 2. So for subsystem 2, it can be written as the same del S by del U for subsystem 2 times delta U for subsystem 2 plus del S by del N for subsystem 2 times change in the number of molecules. Similarly, del square S2 can also be further written as del 2S times del U squared for subsystem 2 times del u2 whole square plus twice of del 2s by del u del n for subsystem 2 times del u1 del u2 sorry del n2 plus del 2s by del n square for subsystem 2 times delta n for subsystem 2 whole square, right. Now we also know that this entropy is an additive property. So entropy of subsystem 1 plus entropy of subsystem 2, it will lead to total entropy change within the system. So what we can write here is that change in entropy is equal to change in entropy for subsystem 1 plus change in entropy for subsystem 2, and further you can use the same set of equations to write. So yes, so first I am writing it for delta S, which is the change in entropy for the total system, its first derivative is equal to delta S1 plus delta S2. Now delta S1 is given in this equation here, delta S2 we have also written here, right. Now we know one more major factor is that this is a closed, overall the system is a closed system. It means that number of molecules of the system is conserved. So any changes which occur in the number of molecules in subsystem 1, it will be equal to minus the number of molecule changes that occur in subsystem 2, that is written here. Similarly, we can say the same thing for the energy because system is isolated. So now using this equation and using this equation along with these terms, what we can do is we can write it for delta S. So delta S can be written as, so what I'll just try to replace these terms with minus of del u1 and minus of del n1. So that will help me to further simplify this equation. I can write it as delta S by delta u for subsystem 1 minus delta S by delta u for subsystem 2 times del u1 plus del S by del n for subsystem 1 minus del S by del n for subsystem 2 times your del n1. Yeah, right. So remember we are trying to evaluate what would the change in the entropy in the system, right. So we have to find these relations del S by del u and del S by del n, and that we can do by using du is, let me go to the next slide. Yeah, so the same I have written here, and that we can do by using the equation du is equal to your TdS minus PdV plus mu dN. Now for constant number of molecules and constant volume, we can simply write del S by del U for constant N and V is equal to 1 by T, and for constant internal energy and constant volume we can write del S by del N at constant U and V is equal to minus mu by T, that we can write from a state equation. Now just replace these del S by del U and del S by del N terms by these variables. What we can get is del S is equal to 1 by T and V for subsystem 1, sorry, is not required, minus 1 by T for subsystem 2 times del U1 plus this one minus mu by T for subsystem 1 minus of mu by T for subsystem 2 times del N1. This is what we get for the relation for the entropy. Now our initial assumption was subsystem 1 and subsystem 2, they are in equilibrium, and the implication it had is that T1 would be equal to T2 and your mu1 would be equal to mu2. So all these terms would turn out to be 0. So we can say that your delta S is equal to 0. So delta S is 0 is when the point is at equilibrium. So it means that our system is in equilibrium. Now to see if the system is stable or not, we have to further check if this is the point of maxima or not, because entropy has to be maximized. So then we take in the next derivative. So next derivative was del 2s, and we write it as a sum of del 2s for subsystem 1 plus del 2s for a subsystem 2, right? It is given in this equation. Now we know that to simplify our calculations, we know that S, N and U, all these terms are extensive properties. It means that they depend on the size of the system. Now since they depend on the size of the system, we can use the scaling with the size of the system to see what each of these terms they hold to. So that's what we are going to do next. We can write del 2s by del u by del n for subsystem 1 as scales with size of subsystem number of molecules in subsystem 1 by number of molecules in subsystem 1 times number of subsystem molecules 1, and this will cancel out, it will be just 1 by n1. Similarly, we can do it for subsystem 2, and when we take the divide this by subsystem 2, we get this term. And now this we will do for all the other terms which are present in the previous equation, where we are trying to find if this is a point of maxima or not. So on doing that, we can, so we have now done that, and now we are left with this equation. So now we have, you can see that all our subsystem 2 terms are vanished here, because we have converted it, we have taken this n2 for that, and we are writing just in terms of subsystem 1 terms. To further evaluate this, what we do is we take this into the denominator side, and this is what we get, and this is equal to some terms here. Now to further simplify it, what I need to do is that I need to see which of these terms they can be negative, right? So I write this equation in this form: del 2s is equal to psi 1 times a positive term plus psi 2 times another positive term, because square term is always positive. So now the sign of this term, it is only dependent on the size of sign of psi 1 and psi 2. But what are these psi 1 and psi 2? So using simplification, we can write that psi 1 is del 2s by del u square, and psi 2 is equal to del 2s by del n square minus del 2s by del u del n whole square over del 2s by del u whole square. Now let's evaluate first what is psi 1. So psi 1 is del 2s by del u whole square. Now in the previous slides, we found that del s by del u is 1 by t. So we take its double differentiative, and we get minus 1 by t square del t by del u at constant n and v. Now the sign of temperature T is absolute temperature, it will always be positive quantity. Now if this term comes out to be positive, then we can say that psi 1 is negative, else psi 1 would be positive. So let us see if this del t by del u at constant n and v is a positive quantity. To evaluate that, we just reverse the term. So we just write it as del u by del t, because we know that leads to your heat capacity. So we write del u by del t, and we write this u in terms of specific terms, and in the end it turns out to be n by Na times Cv. Now we know that Cv, it must be a positive quantity. N is the number of molecules, again a positive, and N is also positive Avogadro number. It means that your psi 1 would be a negative quantity. So the first thing is fulfilled, is that this psi 1 is a negative quantity. Now we have to see if psi 2 is negative or positive. It's negative, it's good. If it's positive, then we have to see which two terms are dominating one. So using the same set of equations, we can reduce the psi 2 term to this term, minus 1 by t del u by del n, and del u by del n is the term which you have seen in the variance of number of molecules, and variance is always a positive term, because this kbt in positive, it means that del n by del mu will always be a positive. So this means that psi 2 is again a negative term. So now we know that del 2s is a negative term, times some positive term plus a negative term times some positive term. So this is how we can define the stability criteria. Now we have proven that del 2s is less than 0. It means that s is at a maxima. So with this we come to the stability criteria. So a system is said to be stable and in equilibrium if its Cv is greater than 0, which is always the case. Also del mu by del n is also greater than 0. This is the necessary and sufficient condition for the system, for the condition of the stability of a pure fluid system. It is a, if these conditions are fulfilled, then we can say that our system is intrinsically stable. We can also write this term here using the Maxwell relations in terms of pressure and volume, which will further give us the criteria for mechanical stability. So we can write del mu by del n is equal to minus v square by n square del p by del v. The first criteria, which is Cv greater than 0, it is called the criteria for thermal stability, and del p by del v less than 0, it's the criteria for mechanical stability. So if these two are fulfilled, then our system is stable. Now let us examine the role of this criteria in the behavior of real system. And for that, let us assume a real system. Let us assume that our steam, it is expanding through a nozzle, and this steam is in superheated form. So this is our nozzle, and the steam is expanding from this nozzle. Let's say that at any point it is at 1. Let me also draw the TS diagram for this situation. So this is TS diagram, this is your dome, and initially let's say the steam is at 0.1. Now as this is expanding irreversibly, we should expect that as it reaches 0.2, the phase change should occur, right? So because this is a saturation vapor curve here, so from steam it should convert back to the liquid. But in real condition, what we have observed that it occurs further, we go down, so it will occur probably somewhere here. Also you see during the boiling is that boiling, it never starts at 100 degrees centigrade. It always starts at certain amount of superheat. That's what we have discussed yesterday also. So why does that occur? What are these states? Are these stable states? Because if we talk in terms of your phase diagram, as per phase diagram, the boiling should occur at 100 degrees centigrade, right? But that doesn't occur. So what are these states? What are these metastable states that we will discuss now? So to discuss that, let us see a PV diagram here. And on a PV diagram, these metastable states, they can be visualized as lying on the isotherms that extend into the vapor dome. So these metastable states, they can be somewhere here on the isotherms which are extending into the vapor dome. And if we begin with a metastable liquid, let's say at this point, and we increase the specific volume, we expect to reach near the vapor saturation line, right? So if we connect the locus of all such points, it means that these two curves or these lines can be connected by a dotted line here, right? Of course, we will discuss the spinodal in the next slide, but first let's use the Gibbs-Duhem equation to further evaluate on what the shape of this dotted line would be and how we can evaluate that. So Gibbs-Duhem equation is a very important equation which relates the chemical potential with temperature and pressure, the thermodynamic variables. If we integrate this Gibbs-Duhem equation, let's say this is your point A, let's suppose this is point B, let's say this is point F, and let's suppose that this is your point G. Now let me integrate this Gibbs-Duhem equation between from point B to F. So I'll just integrate it from point B to point F. d mu is equal to, now since our this is isotherm to temperature is constant, so this term would be 0, and we are just left with your V dP, and from V dP we can write it as from state B to, from point B to F, right? So this will further give us as mu F minus mu B is equal to V dP from point B to point F. Now we see that point B, the mu of point B and the mu of point F, they must be equal for the system to be in equilibrium. So this whole term, it would vanish, and what we are left with is B to F, V dP is equal to 0. What it means that if we extend this curve, it must intersect this line BF, and the area which is lying on this side, it must be equal to the area lying on this side. So this curve I denote by BCD, and this is a point E, right? Now we have also discussed in the previous slide that for the system to be stable, your del P by del V at constant, let me write it in terms of specific volume. So del P by del V in terms of temperature, it must be less than 0 for the system to be stable. Now if you closely follow this curve here, from B to C, it is negative. From C to point E, this is positive. It means that for this region is inaccessible during the phase change. So whenever will be at this point, if any perturbations occur here, we directly transition to this point. And if we take the locus of all these points for different isotherms, we get a very clean curve, and this curve is called the spinodal curve. I think I have this curve on the next slide as well. Yes. So if we take the locus of all such points on the different isotherms, we get this curve. This is called the spinodal curve. So between this curve, the system is inaccessible. We cannot reach to this term. But here we are, you can see that we are in a superheated liquid state, but a phase change hasn't occurred yet. So this is called the metastable superheated liquid. Similarly, on the vapor side, we have a metastable superheated vapor region. So it means that when the condensation is about to occur, we can still have steam at this point or this point, and then if enough perturbation is given, it can transition to directly to the stable liquid region, or vice versa. If we boil the liquid, we can have metastable liquid until this state, this state, this state, and if enough perturbations are given, then it can transition to the stable vapor phase, right? So spinodal limit is the limit or the locus of all the such points which are defined by the intrinsic limit of the stability, and region between the liquid and vapor spinodal curves, they are inaccessible in the system. Now let us try to bring one more perspective on the phase stability, and that too by considering the variation of your chemical potential with pressure. So for that, let us also again start with the Gibbs-Duhem equation. So using the Gibbs-Duhem equation, let me start with point A this time. This is a variation from chemical potential and pressure, and let's say that initially I am at point A. This is your point A. So using the van der Waals equations, P is equal to where R by M T over V minus B minus A by V square, and then putting this in terms of V in this equation, we can see that your pressure, as the pressure is decreasing as you move from point A to point P, your mu would also decrease, right? Further, until point C, we can see that the mu is decreasing. So this is point C, this is your point B. Between point A and B, this region is called as stable liquid. Point B and C are still accessible because they are metastable states. So C and B, it is the metastable liquid region. Similarly, if we do the same for the other side, we can say that point B and F, they are at constant chemical potential, So we can from point B to point point F to point G, this would be the curve, and this would be the metastable region until point E. So we can write that Bg is your stable vapor, Fg is your stable vapor, and Ef is your metastable vapor region. We also see that C and D in this curve is also joined. So CDE can be given here, and CD, this is your D point, CDE. Now this CDE is not accessible to the system. So any state they can be present here, here, or anywhere on the curves between C and A, or anywhere between E and G. But this C and D is not accessible to the system. Now let me assume 2 points here, or next slide maybe. So let me assume a point here, P1, and on this point P1 we can have 3 different states. One can be state A, one can be state B, one can be state C, for which we have different chemical potentials. Of course the temperature is same because this is isotherm and pressure is also same, but we can have 3 different potentials here. Now for the point A, your del P by del V is greater than 0. It means that here the system is mechanically unstable. So that is point is inaccessible. So the only comparison which is left is between point B and point C. Now let us assume that we are heating a liquid. Sorry, no, we are not. Let us assume that the pressure is being reduced from point A. It reaches at point B where the phase change is expected, but phase change doesn't occur there. It then reaches the point B, which is still in the metastable liquid region, and for this point we have some mu, let's call it mu B. Similarly for point C we have some mu which is mu C. Now mu C here is less than mu B. It means that point C is at more stable state as compared to the point B, and of course still as point B is a metastable state and point C it lies on a stable vapor curve. Still the transition will not occur unless we give enough perturbations so that the energy is sufficient for the state to reach from point B to point C, and that usually occur if we reduce the pressure further below PC value, because below further PC we don't have any metastable state. So then the transition will occur to C point. If the perturbations are not enough, in real system this transition doesn't occur, but we have to reduce the pressure below PC. Only in that case the transition can occur. Similarly can be said for the point P2. So again for the point 2 we have 3 points, point A, B and C dash. Point A dash is again lies on the inaccessible region. Here your mechanical stability criteria is not fulfilled. It means that this point is not accessible. But here again the competition is between point B and point C. So let us suppose that we have some steam which is at point B. Now again point B dash here is at a higher chemical potential than point C dash, and it is ideal that the chemical potential it reduces. But still this transition will not occur unless we exceed pressure PE, so that it intrinsically, because after this we don't have any metastable state, only at that state the transition is possible. So in summary what we can say that as per the classical thermodynamics, we assume that phase change it would occur at equilibrium saturation conditions, but in reality the pressure changes at constant temperature, it pushes the system into a metastable state, and deeper is the metastable state, the magnitude of the del P by del V it decreases. It means that it leads to more higher fluctuations in terms of number of molecules and density of molecules as well as the energy of molecules, and that fluctuation it makes the case more likely for the transition to occur. We also discussed about the spinodal limit, which marks the boundary beyond which the phase change is almost certain. After the spinodal limit we see that the system is inaccessible, so the phase change occurs, and actual phase change transformations depends on the likelihood of the triggering perturbations. How strong your perturbations are, only in that case the phase change can occur. In the next class, here we did not discuss anything about the bubbles or the formation of interfaces, but in the next lecture we'll also try to bring in the formation of bubbles, formation of homogeneous nucleation, and then we see what is the criteria for stability and equilibrium. So with this, I would end this lecture. If you have any questions, we can discuss them. Thank you. I know it was a little bit heavy for you. Yeah.
So the perturbation which we have discussed, whether it is a mechanical perturbation or is it a thermal perturbation?
I think it will be a mechanical perturbation. But yeah, so yeah, it will be a mechanical perturbation. So I was just thinking about one case where we happened to see the nucleation of nanobubbles inside a pore. In that, what happens is that we consider a solid state pore, and this is a nanopore. This is very small in size, and then we fill the whole of the tank with any electrolyte solution having some ions, and we apply electrode across this tank. So the only way from which the liquid of this tank can interact with the liquid of this tank is through this nanopore. This is, let's suppose, 500 nanometers in diameter. And then when we switch on the electric field, because of the Joule's heating, because of the electric field, the movement of the ions, it starts. And because of that, the Joule's heating, it develops. So here we see fluctuations between your bubbles, which is homogeneous nucleated, and one which are on the walls of this nanopore. So I was thinking in that sense, but I think the answer to your question would be mechanical stability, because we are talking about del P by del V, the whole regime.